This is a lesson for Algebra 2 for simplifying radical exponents. And the objective for this lesson, students will simplify algebraic radical expressions. Prior to this, students were able to, or you should be able to, just simplify numerical radical expressions. For example, you had a square root of 4. You know that the index is 2, so you're asking yourself, what times itself twice will be able to come out of the radical expression. So we know that if we simplify 4 or factor it, it's going to be 2 times 2, and the index is 2. So we pair up numbers in pairs of 2 since the index is 2. When this happens, only one out of all the paired up numbers will come out, and 2 is the only one that comes out in this example. Today what you're looking at is, what's the square root of a squared? Well, in this example, we know that the square root of a squared is like saying the square root of a times a. And we pair up like terms together, so a times a could be paired up, and only one a will make it out of the radical, so the radical ceases to exist after we pull it out. So a is your answer in this example. So that's where we're coming from. So let's do the next examples as a review of today's lesson. Looking at example 1. When we look at example 1, it's similar to the previous example. First step, we want to look at the index. Our index here is not listed, so since it's not listed, we could assume it's 2. Step 2, factor the radicand. So when we factor, we figure out that the second root of 4x squared is like saying 2 times 2 times x times x. Okay? And since the index is 2, we pair up terms in 2's, okay? So this pair of 2's, one of them gets canceled out, one of them comes on the outside. So we bring one on the outside, which is a 2. The pair of x's, one of them gets canceled out, the other one comes out. So we put a multiply sign by the 2 on the outside, and then put the next term that we brought it, which was the x. Step 4 would simplify, so this we know is going to be equal to 2x. Continuing, number 2. What's the square root of 4x to the 6th power? Step 1, find the index. The index is 2. Step 2, factor the radicand. So this is like saying, what's the second root of 2 times 2 times x times x times x times x times x times x. Index is 2, so we pair up all the pairs of terms. Looks like everyone has a pair. One out of each pair will not make it out of the radicand. So we have 2 times x times x times x, which our answer is going to be 2x to the 3rd power. Now, x to the 6th is a long thing to write out, so another way you could have done this is, instead of showing 2 times 2 times x times x times x times x times x times x, you could have written it as follows. I'll just do it right underneath. You could have written 2, the second square root of 2 times 2 times x to the 3rd times x to the 3rd, right? When we do this, we get the same answer. These two pairs of terms get paired up and they get canceled out, leaving just 2x cubed as your answer. Now, we are almost done here, so it comes to our next step, which is the absolute value sign. We need to know if we need to apply it here. We apply the absolute value sign if, first of all, we need to check if our index is even. Is our index even in this example? It is even. Therefore, our radicand, we want to maintain a positive radicand, which means our root needs to say positive, okay? Since 2 is positive, that's okay, but we look at next at any variables that could make our root negative, okay? If x was negative here, it'd be negative x times negative x times negative x, which is going to leave it as negative x squared. We do not want that. So what we do to prevent that is we put the absolute value sign down around it. This is going to maintain a positive root whenever we need to have a positive radicand. Continuing on number 3. I'll erase the other ones. Okay, number 3. What's the third root of a cubed b to the 6th power? A cubed b to the 6th. Well, in this example, we're going to use a little shortcut. We could write out a to the 3rd 3 times and b to the 6th 6 times, right? But this is going to take a long time. I'm already getting tired of doing this, right? So I don't feel like doing this. I'm going to erase my work here. Erase my work here, and I'm going to start again. Here's the trick. What you do is you take the exponent on the inside, which is the 3. Let's focus on this 3 first, and divide it by the index on the outside. Okay, so in this example, let's do the first one. A to the 3rd. We do a long division problem, 3 divided by 3. We know it goes in there once perfectly, and we only have no remainder. So since it goes in there perfectly, we could take out a automatically. And since we know it went in there once, we can leave it a to the 1st on the outside. Next, we look at b to the 6th. We do the same process. We have 6 divided by 3. And we know it goes in there perfectly twice. So it'll be b to the 6th, or b to the 2nd power. Now we're almost done. We need to simplify, so it's going to be ab squared. Now, we want to see if we need to apply the absolute value sign. So we have the cubic index, or a third 3 as our index on our radical sign. Since it's cubed, it's okay that our radicand is negative sometimes. It's not negative in this instance, but it can be negative. So since it can be negative, it means we don't have any sort of imaginary roots. And so we know that we don't need to apply a absolute value sign. That was number 3. Continuing to number 4. Number 4. Erase these other ones so we have some space to write here. Number 4 shows the 4th root of x to the 4th, y to the 8th. Again, we could apply the same rules as last time. X to the 4, we think 4 divided by 4 is going to be 1, which means all of these 4x's will be coming outside. So we could even just draw it as showing as x to the 1st is coming to the outside. 8 divided by 4 is going to be 2, and there's not going to be any remainder. So it's going to be y to the 2nd. This is similar to the last problem. We have x, y to the 2nd power. Now, in this example, we have an even radical index. Since that's the case, we want to maintain a positive radicand. So we have to ask ourselves, in our answer, are there any variables here that can make our answer or our root negative? Because we don't want that. So if we had a negative x, well, negative x would cause this whole answer to be negative. But what if we had a negative y? Well, y as a negative would be squared, so y negative times a negative would still be positive. So we're not really concerned about the y being negative, but we are concerned about this x being negative, so our answer would be absolute value of x, y squared. Next example. The next example, we have square root of 4x squared, y to the 4th. Okay, our index is 2. We know that the square root of 2, or 4, is 2. We know that 2 divided by 2 is going to be 1, so 1 x to the first will stay on the outside, and y to the fourth will become y squared. And we now look at simplifying this, so we have 2x y squared. I left a little space because I'm already seeing that we're going to need an absolute value sign because we have an even index. Looking at now the variables in our answer here, do we have any variables that could potentially make this a negative answer? Yes, we do. We have x to the first. We want to make sure we have an absolute value sign around that. Okay, last one, number 5. Okay, number 5. Here comes a little bit more of a difficult one, not too much more difficult. So x to the 8th divided by 4, we're going to have x squared. Y to the 12th, we divide 12 by 4, and we get 3. So it's y to the 3rd. Okay. Now we simplify. Looks simplified to me. Next, we need to check our index. Our index is even. Therefore, we want a positive radicand. So we want to make sure our answer doesn't have any variables that could potentially make it negative. So we're looking for odd exponents. 2 is even, so we're not too worried about that because anything times itself in an even amount will be still positive. But we have y to the 3rd here. If we have a negative y here, it's going to become negative, so we want to make sure we put absolute value sign around that. Alright? And this concludes our lesson on simplifying algebraic radicals.